on character oriented framing and bit oriented framing. The first example which I am going to discuss today is just I am going to read the statement, that is on character oriented framing. First one is use byte stuffing protocol and byte stuff the following frame payload in which E is a escape byte, F is a flag byte and D is the data byte other than the escape or a flag character. I am going to write that. So this is what is the message that is generated by some sender. Yes, so we need to stuff this. Okay, so already I discussed regarding this particular stuffing in one of the videos. So where we were using the stuffing technique to separate my special characters from actual flags. So in this case, this is what is the message that is generated by some sender, some sending entity. We need to stuff this. Look at this message in which we are, say, encountering some special characters which are used for some special purposes. Especially the character F is used to identify the frame delimiter. But in this case, this character F is also a part of the data. Now I want to provide some kind of an indication to the receiver that this is not the flag. For that reason, we are using a stuffing technique. Okay, this was already discussed in the last video. Now we need to stuff this data with a proper characters. I'll start that. First D. Now you see, I am encountering a first special character to tell this is a special character to the receiver. Okay, we are stuffing additional character E before the actual E. Yes, so the red colored one is the stuffed character, and next is a D. Again you see we are encountering one more special character, that is E. So this will going to be stuffed by using an additional special character E, and again that actual E, then one more special character, that is E. This is going to be stuffed by one more E, and next is F, flag character. That too will going to be identified with the help of E stuffing. D and E, F, D. So look at the number of stuffings we have done, where all special characters such as E and F appears in our data part. All those will going to be stuffed with additional characters. Okay, so here we are using a additional character to identify this is a data character. So this is, because of that we are calling it as a character oriented framing or byte stuffing. Since each character is represented by using a one byte, so we are sometimes we also refer it as a byte stuffing. So this is one example of byte stuffing. Now I will talk regarding bit stuffing. Example on bit stuffing. Fine. So let us consider one example in which I have a bit stream like this. Okay, this is what is the bit stream which is generated as a part of the data. So I need to use, say, bit stuffing technique over here. This is an example on bit stuffing. So how exactly to stuff? According to the rule, after 0, if 5 ones gets encountered, okay, you need to stuff one additional 0. Now the rule is slightly different in case of bit oriented protocol. In the previous case, I used to stuff a character before the special character that was part of the data. In this case, I am going to stuff a 0 after those 5 ones. Okay, I'll just show it over you, show it that thing over here. I'll, for understanding reason, I'll add one over here, so that I can, say, show you that stuffing. In this case, you see this part where you are getting 5 ones after 0. 0 followed by 5 ones. It is required to be stuffed. Okay, according to the rule, you need to stuff one additional 0 over here. Yes. Thereafter, remaining bits, that is 4 zeros. Yes. So this is additional 0 which will going to be added over here just to separate this particular thing from the flag. Now next, again you see we are encountering 5 ones after 0. It is also required to be stuffed. Okay. So 5 ones, it is going to be stuffed with additional 0. Yes. Thereafter, we are going to have 3 zeros like this. Then again you see you are coming across 6 ones. So how exactly this will going to be stuffed? So according to the rule, you need to stuff a 0 after 5 ones. Okay. So 0 followed by 5 ones will going to be stuffed with 0, and then next bit is 1, and rest all the things are as it is, because here last we have 4 ones and 0. This is what is a frame which will going to be looks like after stuffing. Okay, this is what is an, say, way of stuffing the bits in a, say, bit oriented protocol. Fine. So now we'll go to discuss de-stuffing activity. How exactly de-stuffing happens at a receiving side. So this is what is action that is happening at a sending side. Now I will talk regarding de-stuffing activity that happens at a receiving side. So these are all the issues that are related to the framing. As it was told to you in the last class, okay, framing, one of the important technique is, one of the important thing is that we need to, say, add some special bit streams to identify the beginning and end of the frame. Okay, now to, say, overcome the confusion of if same kind of a bit stream appears in the data part, how to identify that? For that reason, we are providing a tool of bit stuffing to the receiver, so that receiver can identify these are the part of data. Okay, now how exactly receiver deals with these type of a stuffing at a receiving end? Okay, we'll take one example on that, how exactly receiver will go to de-stuff that. Okay. So consider a bit stream which is already stuffed. Okay, so Now we'll talk regarding de-stuffing activity. Say this is my stuff frame. Okay, I need to de-stuff it. Okay, at the receiving side, this de-stuffing activity happens. How to de-stuff it? Okay, as I told, what rule we are following to stuff, opposite of that will going to happen at the receiving side. Okay, according to the rule, so if 0 followed by 5 ones, the next 0 is what? It is considered as a stuffed 0. Okay, so in this case you see 0 followed by say 5 ones. This is the stuffed 0 which will going to be removed by the receiver. Yes. Now you take in rest of the cases you are not finding any such combination. Only over here you are finding one more such combination. You see 0 followed by 5 ones is again say ending with additional 0. So that 0 is now stuffed 0 which will going to be removed by the receiver. So this is how the receiver will going to eliminate these stuffed zeros from the data part. Yes, this is the case with bit oriented protocol. Fine. So same is the case with byte oriented protocol or character oriented protocol. Okay, so we'll consider one example on byte oriented also. So in case of byte oriented protocol, you see if this is my data pattern, okay, if this is my frame which is received by at the receiver side, which is of the type character oriented protocol. So how exactly de-stuffing happens, that we're going to see. Now see, as it was told to you, okay, whenever some special character appears which will going to be stuffed with E. So in this case stuffing happens before that character. Okay, so in this case you see this is what is the E, okay, which is going to be stuffed by a special character, that is E. This is the stuffed character. Fine. Now come at, say once we start moving over here, we are encountering F, EF. So since there is no E before this, so that means this is a stuffed E which is appearing before F. So this E will also going to be removed from the say this data frame at a receiving side. And again you see this kind of a situation is again over here where we have a E which is stuffed before F. Yes, and one more such situation over here where we are finding two E's. So this is again a stuffed E. So I am removing it. So in the end the receiver will going to receive this as a data. So this is what is the data that looks like after de-stuffing. Fine. So this is regarding stuffing and de-stuffing. I hope it is clear to you people. So these are the example, and later I will go to post one assignment to you people which is connected with stuffing and de-stuffing. Okay. So now we'll move to examples on FSM. Yes. So we'll discuss few examples which are connected with finite state machines. Okay. So in one of my previous videos I discussed regarding this FSM, and in this under this title I discussed two protocol. One is simple protocol and the second one is stop and wait protocol. These two I discussed in the last video. So for understanding reason I will repeat few points of stop and wait because my next example is based on that. Okay. So first, one thing you need to know regarding before creating a FSM, you should know how exactly that protocol behaves first. So based on that itself the FSM is going to be say created. So it was told to you in stop and wait two entities will going to be there. One is a sending entity, yes, and another is a receiving entity, R. Yes, job of a sender is to send the frame. Since I am talking regarding the data link layer, I will going to use the term frame. So the frame is constructed only when a sending side entity receives the packet from network layer of the same machine. Right? Once it gets the packets, it constructs its frame and sends it to a receiver. Okay. Moment the frame appears at a receiving side in a healthy condition, receiver will acknowledge that by sending an acknowledgement frame. Okay. So till that time, the sender is not doing any activity. The job of a sender is to send a frame, wait for an acknowledgement. So during this period, even though the data comes from the higher layer, sender is not responding to that. So that means when I talk of say sending a frame, and after sending the frame by the sending side, what exactly will be the state of the sender? Sender is in blocking state. So moment it sends a frame, it is entering into the blocking state and it is waiting for an acknowledgement that is appearing from receiving side. So moment it sends the frame, it will also perform some other tasks while sending the frame. So it sets the timer. Yes. So it is setting the timer and it keeps the copy of the sent frame in a buffer at sending side. Yes. Then it sends it. So moment it appears at a receiving side without errors, the job of a receiver is to accept it, hand it over to the network layer on receiving side. Okay. So it is accepting this frame, checking it for errors. If it is passes through the test, it extracts the packet that is present in this frame and hands over it to the network layer. After that, it sends the acknowledgement frame to the sender. So normally this acknowledgement is indicating which is the next expected frame at a receiving side. Okay. So to carry out this particular exercise, what we need is we need a support of sequence numbers. So whenever a frame is sent from a sending side to a receiving side, it will also include a sequence number apart from the addresses in the header part. Okay. One of the important information that header contains is a sequence number. Now you see the scenario in stop and wait. The sender is not sending a new frame until it gets an acknowledgement from the receiving side. So for that reason, I don't need a sequence number with many bits. My sequence number will be indicated using only one bit. So in this case, only one bit sequence number is enough for us to convey the messages. So whenever you are sending a sequence number 0, the receiver is, if receiver is waiting for sequence number 0, it will go to accept it. And it sends an acknowledgement saying that it is expecting a frame with sequence number 1. Okay, this is how a stop and wait works. And whenever there is loss of frame, or if frame appears at a receiving side with some errors, how exactly receiver will go to react to that? So whenever the frame is lost, there is no question that receiver is not getting anything, so it has to keep quiet. But if this frame, if it comes at a receiving side with errors, how exactly receiver deals with it? Simply it discards this. Simply it discards the frame one which comes with error. Fine. And it will not going to send any acknowledgement to the receiver. I mean to the sender. Clear? It is not sending any acknowledgement for the received frame, because the frame one which is received at a receiving side, if it contains error, it keeps quiet. It discards that and it keeps quiet. Now by doing so, it is indirectly conveying a message to the receiver that its frame is coming with some errors, or there is some problem with the frame what it has sent. Clear? So how exactly the actions will take place for this type of a activity? You see, moment it comes over here with an error, it is discarding it and it is keeping quiet. So what happens at sending side? Sender is waiting for an acknowledgement. How much time it will go to wait? It will go to wait till timer gets resets, till timeout occurs. Moment timeout occurs, now the sender will going to resend the same frame, concluding that something is wrong with the sent frame. This is how it takes care regarding, say, loss of frame or the frame one which is reaching at a receiving side with some errors. Okay, so resending means it will go to use the copy one which is stored. It will go to resend that. Again, while resending, again it takes care regarding keeping its one copy, and once it resends, again it will do the same activity of setting the timer. All those activities will going to be done. And for this, I also showed you how exactly the FSMs will going to look like. Sending side and receiving side FSMs, I have shown it in a video. Yes, based on the same idea, I'll discuss one dummy example, okay, where I am not talking about any particular protocol. I'm just going to read out the problem statement. Based on that problem statement, I'm going to construct the FSM. Okay, so I'll just read the problem statement. Now, what it says is, according to this problem, using the following specifications, draw the FSM with 3 states: state 1, state 2 and state 3. Yes, and 5 events and 6 actions. There are totally 5 events and 6 actions. Okay, now according to this problem, the first bit what it says is, yes, so that means one thing is clear in this example, that my protocol or whatever it may be, FSM, it has a 3 states. State 1, I will represent it as S1. State 2, I am going to represent it as S2, and the third one is S3. These are the 3 states, and I will consider the S1 as my start state. With that assumption, I will start. Yes, what exactly the first problem statement says is, if machine is in state 1, 2 events can occur. If event 1 occurs, the machine moves to a state 2. If event 2 occurs, machine performs action 1 and 2 and moves to a state 3. So, according to the statement, if event 1 occurs, say the machine moves to a state 2, and if event 2 occurs, machine moves to a state 3. Okay. So, when it is in this state, I will consider this as a start state. So, according to the problem statement, what it says is, if event 1 occurs, it moves to a state 2 and there are no actions happen associated with this event. Fine. And when event 2 occurs, it moves to a state 3. Yes, performing action 1 and action 2. I am representing these actions as A1 and A2. So, whenever event 2 occurs, machine is changing its state from S1 to S2, okay, by performing actions A1 and A2. Is it clear? Okay, so if machine is in state 2, now I am talking regarding a situation of machine being in a state 2, yes, and 2 events can occur. If event 3 occurs, machine remains in the state 2, and if event 4 occurs, machine moves to a state 2. Yes, when event 2 occurs, it stays back into a state 2. Yes, I mean event 3 occurs, it stays back into a state 2 without performing any actions. And if it is in a state 2 and event 4 occurs, yes, if event 4 occurs, it moves to a state 3. Yes, and again there are no actions performed. Fine. And one more thing, like if the machine is in state 3, 3 events can occur. If event 2 occurs, the machine remains in state 3. So that means if there is event 3 occurs, it remains back in the state 3 without performing any action. And if event 3 occurs, the actions 1, 2, 4, 5. Okay. If event 2 occurs, machine performs 1, 2, 4, 5 actions and it moves to a state 2. These are the 4 actions which are going to be performed when event 2 occurs when machine is in a state 3 and it moves to a state 2. And if event 5 occurs, machine performs action 1, 2 and 6 and moves to a state 1. Yes, if E5 occurs, say it is performing action 1, 2 and action 6 and it is moving to a state 1. So this is an FSM example. So as I said, it is nowhere related to any of the protocol. This is just an example of FSM. Okay, I hope it is clear to you people. So this is one kind of an experiment which I performed to take a live class. So in the next class, okay, I am going to discuss regarding HDLC and PPP. Thank you very much.